Okay, recording started. So how do I get the screen here? Krzyś, how do I get the screen here? Robot. Okay. Okay, great. All right, so this is my great honor and pleasure to introduce Damian Osajda. He confirmed that what ChatGPT wrote about him is actually correct.
We'll see.
He's the full professor at the University of Copenhagen, of course, Department of Mathematical Sciences, since 1st of June 2024. But originally, academically, he comes from Wrocław. He was on the faculty of the University of Wrocław together with Emma for many, many years. I remember giving a talk at your seminar in Wrocław.
That's correct.
And when it comes to his academic background, actually, I'm very happy to say that he got his PhD in 2004 from INPAD, right? So that's the institution where we are, gave him his PhD. And his early career included postdoctoral positions in Paris, Berkeley, Strasbourg, Lille, and Montreal. And now what is very important that you realize that his research focus is geometric group theory, particularly groups acting on spaces exhibiting non-positive curvature-like characteristics. And he's a recipient of many prestigious awards. So for starters, in 2020, he received INPAD's award, the Science Prize for Outstanding Achievements in Mathematics. Just a year later, he received the main Stefan Banach Prize from the Polish Mathematical Society. So Jacek is the guilty person here. Well, I find it really impressive. He, like Rita, is very good with getting funding. So for the years 2023-2026, he is awarded 4.9 million Danish crowns from Carlsberg Foundation.
Yeah.
I wonder how much beer I can buy.
Yeah, I couldn't bring any beer. I mean, beer is not included. At least I don't know. I mean, they didn't say anything. Although there is beer, Carlsberg beer, with the same name, exactly the same name, Semperande, Ardens. So.
Yeah. And his project is groups and non-positive curvature. Okay, I think this is enough as far as introduction goes. Without any further ado, ladies and gentlemen, I'm giving you Damian Osajda. It's all yours. Take it away.
Thank you very much. Thank you. Thank you. So thank you for introduction. It's nice to learn about myself something, and thank you for invitation at all. It's always nice to speak to young people. Okay, so I tried my talk to be elementary, and so I know that some of you may expect more elementary talks. Some of you are more experienced. So if you want to please everybody, you probably fail everybody. So it's what I'm planning to do. So the talk is elementary. The talk is elementary. The title is not that elementary. Non-positive curvature seems maybe a bit frightening, but don't worry. I mean, we'll start really slowly and then we'll go hopefully far enough. Okay. So let me just start even with the definition of a group. I mean, this is just definition of a group. I don't like this definition because we do other things in geometry group theory. But this is this formal definition. Group is a set with operation, binary operation. There is identity. I call it identity, right? Or neutral element, this guy. Sorry, this guy here. And then for everyone, I didn't write all the quantifiers here, right? But we are adults already, so we know what's this. This is just for a reminder. So for every element, there's this. I'm sorry, it's my fault. There is this inverse element. I will denote it like this. Yeah, if I do it, it disappears. So this is just a definition that we all know. It's just for for setting up the notation. I hope everything is clear here. Okay, so here are some examples. I mean, trivial group, just one element, so everything is trivial, as the name suggests. Identity is identity, and so on. The less trivial example, but still trivial, just zip with addition. Cyclic infinite group, I will call it, maybe. Sometimes I call. And so just notation-wise, 0 here is identity, right? 0 here is neutral element, and instead of dot, I have this plus. I mean, not important that much. I hope everything is clear here. By the way, interrupt me in a moment, right? If I'm going too slow or too fast, just interrupt me and yell at me. But be kind. I'm also a human, kind of. So here is the first maybe non-trivial example that maybe does not appear at every algebra course. So this is a non-abelian free group. So what's that? So this is the kind of, in a way, in the simplest group that you can get. You just take, so this is free non-abelian group on two generators. So this AB are called generators. So I will later tell you about group with more generators, free groups with more generators. So this is on two generators AB. So it means that elements, as elements, you take words in these two elements, AB, and also their kind of formal inverses, okay? Inverses, this inverse notation coincides with the notation that we had before. They really correspond to inverse notation. In particular, you better do, you treat A minus one as identity, okay? So in fact, what you can do is you can consider only reduced words where you omit this appearances of A minus one or B minus one or A minus one A. So this is this. I'm sorry. So this is this, or yeah, it doesn't. This or this. You just forget it. You just you just remove this from words. Then the word is reduced. So word. First of all, word is a finite sequence of elements, right? Reduced means without this appearances of this A minus one. And then there is group operation. Group operation is just concatenation of these words. So you concatenate, so write one word after another. In particular, it means that this group does not need to be, and it is not commutative, it's not abelian. If you write W, V is different than VW. And then you reduce, right? So for example, here is here I have example of this operation. So you have these two words, you multiply them, but then you have obvious reductions like this B minus one and then further. And what you get as a reduced word is this ABA, okay? Does make sense? So this is kind of the most basic group in a way, because you have generators. I also want to introduce some notation over the talk, so here I already do. Generators are AB, and then I have and then I know how to multiply them and elements. But now we go a bit further. But like basing on this free group, we can have something which is called group presentation. So you have here generators. So S is a set, some just finite or infinite set of elements that are called generators. And then R is a set of words in these generators and their formal inverses. So this is what this S minus one means. This S minus one means the set of elements in S inverses of those elements, okay? And as before, I take just the words, some words. So this is just a data. Just a set of data. One set, the second set, that's all. However, with this, you have associated a group, which is called, okay, the group defined by this presentation. So here is the formal definition. So I will explain it in a moment, so don't be frightened if you forgot something about groups. So Fs is this free group on S. So once again, reduced words in S and S minus one and inverses. And here you quotient by, this is supposed to mean normal closure of the set R, because our elements of R are words, so can be treated as elements of a free group. So R is a subset of a free group. You can take the normal closure of it, so it means the smallest normal subgroup containing this set in F, and then quotient by it, okay? But this is for those who remember all this stuff with quotient, normal, and so on. And intuitively, what you do is the following, that you, as before, as in the case of free group, you take words in S and S minus one, but then you declare some of those words give trivial elements, okay? So before you declared for free group, you only declared that A minus one or A minus one A is a trivial word, right? By the way, trivial word is the word, okay? It's actually identity in the free group. So here you declare also that words in R are trivial. And they are called relations. And then, so then you operate on such words, again concatenating them, but remembering also that you forget or you delete words from R. Does it make sense? So I believe many of you saw it already, but I will work through this lecture now. I will work on this group presentation for some reasons. So I
ask you just a silly question. So you do not assume that S is finite, right?
No, no. A priori, I do not assume that S or R are finite. But this is a good question. There is a notation. So when S is finite, you say that the group is finitely generated. Some groups can have, okay, so a presentation can correspond, I mean, to one group, you can get many presentations. We will see it maybe. And if you can find presentation with S finite of a given group, then it means that then you'd say that the group is finitely generated. This is an important property of a group. And also, if you find a group such that S and R are finite, so R is a finite set of words, then you say that the group is finitely presented. And this will the question about finitely presented group will appear in a moment. So those are important notations, okay? Notions. But thank you. A priori, I do not assume. Okay, so here are examples of presentations. So, so the first kind of trivial example, you have this one generator A, and here I have empty. I didn't take any elements in R. This is empty. Okay, so I just take A, and then elements are A, and also A minus one, A minus one, A minus one, and so on. Okay. So of course, this corresponds to the group, to the cyclic infinite group, right? Where A corresponds to 1 in Z. Does that make sense? Yeah. So this is the second one. This presentation is, of course, our presentation of a free group on two generators, because I simply do not impose any relations. I just take words, and the only relations kind of that I assume are A minus 1. Okay. Here is more complicated, but still, I believe, clear example. So this is a presentation of Z square. So Z square are pairs of integers with coordinate-wise addition. Okay. So just to remember, just to recall, identity neutral element is 0, 0. Element inverse to AB is minus A minus B, right? And this is given by presentation AB, two generators, and with a relation. This relation is called commutation relation. This is AB, A minus 1, B minus 1, AB, A inverse, B inverse. And you can see it also, you can write it. I mean, so this means you assume that AB, A minus 1, B minus 1, AB, A inverse, B inverse. So saying that this is related, it means that this is equal 1, right? But if you can write the equivalent equation which says that AB is equal BA. So this is just a commutation relation, right? So this is a group given by two generators which commute. So this is a Z square plus. This is free abelian group of rank 2. Does it make sense? Just a notion. Once again. Where is 1?
Use the neutral element, you mark it by 1, not 0.
Yeah. Okay. Sorry, because this goes back to my notation. Yeah, this is why I told you that I like the notation. That I said this notation. There exists 1. Okay. This is just a notation.
Thank you.
Yeah. Yes, because I usually work with non-commutative groups. I mean, commutative groups are
boring.
Let's say it Baldwin. They are boring. Yes, they are boring. They are useless in a way. So I always use the multiplicative notation. Okay. Okay. So let's go. So those are examples presentations. So are presentations okay for a moment? Okay. But as I told you, presentations are not unique, right? You can have one group with different presentation. You can invent them. It is an exercise, easy exercise. So important question is whether a given presentation gives you a trivial group, for example, because trivial groups are even more boring than commutative groups. So we don't want trivial groups, okay? Yeah, I will during this lecture, I will actually address a stronger question, or let's say weaker in a way, namely whether given presentation defines an infinite group, because abelian groups are boring, but finite groups are also boring. And from point of view of geometric group theory, we are really interested in infinite groups. Okay, just take it as it is. Just I'm interested in infinite groups. So for me, the second problem is very interesting: whether a given presentation defines a finite group or infinite group. And I want it to define infinite groups. So this lecture will be about the quest of looking for conditions on a presentation that guarantees that the group defined by this presentation is infinite. Okay. And this is related to at least two famous open problems that I will state here that you can understand, at least after this talk or maybe after some research, more research. So here's the first one. This question is about the so-called Burnside groups. So a free Burnside group, I will denote it by B and M, on n generators. So n denotes the number of generators, and M denotes the order. You will see in a moment what means order. Order means that every element is of this order. So every element to this power M is identity, right? So is given by the following presentation. S is a number, n is a number of generators, and M is an order, which means that in a relators, as a relator, you declare that every word, it means every element of a group, if you raise it to a power M, it will be identity because it's in the set of relators, okay? So this is called the free Burnside group. Once again, unraveling this definition. A free Burnside group is like the biggest group in a way, generated by n elements such that every element of this group has order M. So every element of this group G raised to power M gives you identity, okay? And this is the presentation of such group, okay? Here are trivial examples. If you just raise to power 1, it means that as relators, you write all the elements of a group, all the words. So this is just a trivial group because all the elements are trivial, right? Here's another simple example. If you have one generator and order M, it means that you've got cyclic group of order M, okay? So group, here it's like additive group modulo M. Does it make sense? Yes?
Exactly, order M.
Okay, so this, I mean, as it's written is at most, but in fact, it will be exactly order M, this group. If you think for a moment. This is kind of exercise. Okay, so those are Burnside group, and already here, and already with quite small numbers, there are interesting questions. First of all, observe that the second example tells you that we are not interested in one generated groups. Okay, so better take two generators. And already with two generators, there are interesting questions. Okay, I wrote what I said. So here is an exercise. You know, it's tricky exercise. B22, B23, B24, B26 are finite. So those are all groups on two generators with different orders. I believe 2, 2, so two generated group of order 2, every element is order 2, is known to all of you. You can easily see that it's finite. B23 is maybe more complicated, but you can do it probably on the sheet of paper just during this lecture. B24, I don't know. By the way, I never did. So, and then B26 is finite. This is maybe a bit hopeless, but try.
Why is B22 finite? Can we make any group element of form AB, 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 and so on and so on? So
No. But you say that B22 tells you that every element is of order 2.
Oh,
right?
Okay, yeah, I get it. Okay.
So think about it, but this will be clear now. And here is the funny fact. It's not known whether B25 is finite.
That's incredible.
And this is
That's incredible.
Yeah. And this is an important open problem. I mean, please solve it and you'll be famous, really. I was a bit afraid that maybe it's solved. And I just asked Google. So I will tell you in a moment. This is a bit disclaimer, but don't worry. I mean, if it is even solved, then you should ask about B27 and B28 and B29. And you will see how long you should go. And all of this, and this is open for a very long time. Nobody knows.
Sorry, stupid question. If 5 is smaller than 6, so shouldn't it also be finite? So what is the?
Do you claim you solve it or?
No. I'm not getting something, since if we know that B26 is
those are you know, those are relatively prime numbers. I mean, what has 5 to do with 6? What has order 5 to do with order 6?
So this order should be exactly or smaller or equal than 5 or 6.
No. I say no. I gave you the precise presentation, right? I gave you the precise presentation. Just every word to power 6 should be identity. It doesn't.
Okay, I see.
Doesn't mean that order that every element to power. I mean, okay, if you have, yeah, if you know
so
that
the order is precisely 6.
Yes.
Okay, that's clear.
I mean, if you have B25, you know that every element is of order 5. Yeah, you don't claim that every element, I mean, raised to power, 6 is. Okay, so this is a question. The first question, it's open question. By the way, I was a bit afraid preparing it yesterday. So yesterday I checked still, and so this is just disclaimer. Be careful, right? Be careful when you ask AI. Okay. It's not true what it says. So it says it's known, it's finite, and I dug a bit, just a bit. So where the confusion comes from? I mean, confusion for our friend. So the confusion comes from. So you should notice in particular this number 534. For example, it appears. This number appears. This is one paper on which this answer of AI is based, and it says here, in fact, that there is some 554, and there are other things. So the point is, that this paper tells you that this 554 is the bound on the finite Burnside groups of order 5. Okay. Yes, it must, but finite. If this group is finite, then it has to have less than 534 elements, but it doesn't say it has to be finite. This is actually very interesting. This is related to an open problem that was awarded. Our solution was awarded a Fields Medal, namely this free Burnside group has finite quotients, of course, because we know finite groups of given order. They have to be quotients of free Burnside groups. So the problem was how big can be those finite groups. And actually, this is partial answer that such groups can be have only some size. Okay. This was awarded Fields Medal. Zelmanov got it, I don't know, long ago. Okay. So this is just a disclaimer. Once again, free Burnside groups, B25 is not known to be finite. I don't know how you feel it after your group theory course and your experience, but for me, at first sight, I would say that if you have a finitely generated group, every element has finite order, then this group, and given order, let's say M, this group should be finite. Actually, this was a question posed by Burnside, and this is why Burnside groups, it was posed at the beginning of 20th century, and then it was answered only in 68 by Novikov Adian. Those are two guys, Novikov and Adian. And by the way, notice that N is before A. This is kind of uncommon in mathematics. You always put the authors in alphabetic order. I don't know, this is some Russian, I don't know, hierarchy. Yes, I mean, Novikov was definitely a star then. Adian was some younger guy. So, okay, still, so after 68 years because Burnside really asked this question at the beginning of the century, they answered this question. This is a very, very difficult theorem. And, well, I should say, tadam. The proof actually goes via non-positive curvature, kind of. So this is what this group is, this is what this talk is about. How you can detect whether some groups are infinite, and it is what they did.
Can I
Okay.
question?
Yes.
So what does precisely
Do you have microphone?
what does B2M is infinite for a large M mean? So it means that there exists M that this is infinite?
Yes, let's.
From
You
some
should.
point?
You should. Yes, that's true. You should. There is a story. I didn't want to do it precise because then I would lie, and so I did it imprecise. So the story is the following: that they proved that for odd M, large enough, their large enough was bigger than 1,400, something like this. Those groups are infinite. All of them, all big ones. I think so. Yeah. Then for a long time, people didn't know what to do with even numbers. Finally, people also solved the even numbers case. So back to our question about B25, the best infinite, I mean, the smallest M for such free Burnside groups is infinite is probably 665. So you know, so this is why I told you that you shouldn't worry if 5 is solved, okay? Because you still have few numbers till 600. And this is another big question. I mean, if you reduce this number 650, 65 to let's say 100, it's also very good because it means probably that you invent some new tools and so on. So there is a lot of things here. Okay. Any further questions about this problem? Yes.
Sorry, but there are some cases of odd numbers smaller than this threshold 665, for which this is infinite or not?
I have no idea. Yeah, I'm sorry. I do not know that well the status of this. I do not know what's the lower bound now. Okay. I know that this. I mean, the initial story was that they showed it for odd numbers, 1,400. Then a few years later, Damian himself probably reduced it to odd numbers bigger than 665 or something like this. And then there were some other words. I do not know what's the status now. But this is around this magnitude, around 500, I think.
Okay, thank you.
Yeah, I understand. I understand that you asked this because you don't want to invest time if it's already solved. But I think if you do 10, you are safe. Okay, so this talk is about non-positive curvature, how it can be used to answer these questions like this. And in particular, I want to tell you a glimpse on what kind of condition or what kind of properties Damian and Novikov could use. I will not get into details about this. Yeah, this is another problem. Yeah, I want to mention 2 more problems on Burnside group, important, very important. This is what I told you, just find small ones. And here is one that I find, and the next one is one that I find really, really interesting and kind of central in a sense in a group theory. It's also a very well-known open problem. Do there exist finitely presented infinite Burnside groups? So let me explain it for a moment, something. So first of all, I do not say here free Burnside groups, I say just Burnside groups, okay? So once again, I remind you that free Burnside group was given by this huge presentation. Let's say for relator for 2 generators. We have 2 generators, and then you write all the words to power m, okay? So this means that this presentation is infinite, okay? And it's known that free Burnside groups do not have finite presentation, okay? Free. However, here I say about Burnside groups. So what it means a group in which every element has a given order, but there can be other relations, okay? Before, I told you that the presentation is just that I only impose the relations that say group element to power m is identity. I don't assume other. But of course, as I told you already, I told you about quotients of free Burnside group. There are quotients of these groups, meaning that you can add some other relations, okay? In particular, just as an exercise, for example, if you take free Burnside group and you add relations telling that all the elements commute, then you've got a commutative group in which every element has order m. And this group you will very know. You know very well, right? This is finite. This has to be finite, for example. But there are quotients. So Burnside group means simply quotient of free Burnside group. Does that make
Sorry,
sense?
I'm a little bit confused about one detail. In free Burnside group, every element has the same order. In this Burnside
Yes.
group, every element has finite order, not necessarily the same.
No, no.
Yes?
In Burnside, for Burnside group, I say it has to have the same order. Yes.
The same, still
Yes.
the same.
Yes.
Okay, okay.
So the difference is, Adam, but you can add relations.
Yes. Once again, Burnside group means a quotient of free Burnside group.
Exactly.
Okay, okay, okay.
Okay. But this is a very good question, and this can be also kind of exercise, and so maybe I should make the remark that I didn't do.
Wait. When is the homework due? When I'm supposed to deliver you the exercises solved?
Yeah.
Set a deadline.
Wait. Okay. I set the timer. Okay. Go now.
Go now.
So, okay. So one more, maybe one remark that I didn't put it, but it's important. Maybe I like this remark in relation to this last problem. So I told you, I mean, at least for me, but I believe also for many people, this is quite surprising that there exist infinite finitely generated groups of given order. So now think about this. There exist groups of finite order, right? Finite groups, for example. There exist infinite groups of finite order. I mean, every element has finite order. For example, you can take the direct sum of infinitely many copies of Z2. Okay, but this is infinitely generated, right? So the next question was, in fact, and this was also part of Burnside's question, whether there exists finitely generated torsion groups. So this is what you asked. So finitely generated groups that every element has finite order, but whatever order. And this is nice exercise. I do not know how to solve it. I mean, now there are many constructions. They are quite easy, but still there are not that easy. They use small cancellation that I will show you, or some other tools. But this is already difficult. And then they came this original Burnside problem, whether there exist finitely generated groups with bounded exponent. Okay, and now, so this is like next in the line, whether there exist finitely presented groups of bounded exponent. Actually, it's not even known whether there exist finitely presented torsion groups. So with this exponent, whatever. I mean, different for different elements. This is also open problem, but I wanted to be short here.
Say it again, what the problem is, finite.
Do there exist finitely presented torsion groups? Meaning that every element has finite order, but it can be that the order explodes with elements. Okay. Okay, so that's it for Burnside groups, and for problems, I will now go into non-positive curvature. I mean, into the tools that kind of, I believe, serve to answer questions like this, okay? But for this, we need to, to understand, to change maybe a perspective a bit. So as Jacek introduced me, I'm claiming I'm working in the so-called geometric group theory. So geometric group theory is studying groups, but using geometric means, using geometric tools and treating groups as kind of geometric objects, okay? This is just a slogan for a moment. We'll see what it means a bit. Okay, so how can you look geometrically on a group? So here is one way. You consider the so-called Cayley graph. So I'm trying to be consistent with my notation. So S means, again, the generating set. And then if you have a generating set for a given group G, then you can define the so-called Cayley graph. So vertices are just elements of the group. And then you put edge between elements of the form G and G multiplied by generator, okay? And actually, this is directed edge, because you can direct it just from G to G to S. You say this is direction. This is not that important for me, but just to be clear, they can be directed. This is a graph. Here's an example. So this is our infinite cyclic group. I drew it, of course, like on purpose on the line, right? I mean, this is because this is what I think about this group geometrically. This is a line, and this is a justification why I think it's a line, because one Cayley graph of this group is a line. So this is, so once, just to unravel the notation, because we will use this notation for the rest of the talk, I have here Z, the group Z, and here is the generating set. This group generated, for me, S is generated by one in this additive notation, okay? So you see, so for example, here is identity of this element, of this group, right? Here is 1, here is 2, and so on. And I didn't put labels on the elements because I didn't want to make this picture too blurry, but I put the label, one label, just to say that there is one type of edges generators, okay? Does it make sense? Okay, so first of all, what you immediately see is, or realize, of course, that Cayley graph depends on the generating set, right? So here is an example of a Cayley graph for the same group, but another generating set, right? So here I take 2 generators, 1 and 2. They generate they generate cyclic group, right? There's no, and this is the Cayley graph. They look differently, but in some senses, I will not go into this during this lecture, but this is actually a big theme in my area, in geometric group theory. In many senses, those 2 graphs look the same. They too look like a line, in a sense. One way of seeing it is that you take this picture, you go far, far, far away, and you look at this picture from far away. In the limit, you see a line. But I will not go into this, but those are the tools that we use usually. But I will not.
Or in technical terms, it is called coarsely equivalent. Yes, this is what
That's
you
true.
refer
That's true.
to.
They are even better. There are by Lipschitz equivalent.
Okay.
Coarse is very coarse.
Okay.
Of course.
Of course.
Of course.
This is another thing.
Thank you.
Okay. Any questions? So just let me go through several examples because this will be relevant to what I'm going to say. So here's the Cayley graph of the free group on 2 generators, free non-abelian group on 2 generators relative to this 2 generators, to the generating set, right? So this is just a tree. This is a graph without cycles. We call such graph connected graphs trees. So again, I have identity here, and now I can go, for example, elements of my groups, as I said, are words like A, B, A, B, right? So I could go A, B, A, B. This element would be element A, B, A, B, right? If I do some cancellations, if I go like A, B, B minus 1A, this is the same as if I go A, A, right? So so you see this thing about reducing words in this picture, right? Does it make sense? And again, here, it is this is additional structure on Cayley graph. I will not explore it, but you can. It's not only directed graph. Actually, it's also labeled graph. Where labels edges are labeled. Here you have either horizontal or vertical edges. Horizontal are A, vertical are B, and so on. Right? There is additional structure, but for me, it's important that this is a graph. Okay, does it make sense? Yeah. And this graph is a tree, in particular. Cayley graph of a free group on 2 generators is a tree, a graph without cycles. Here's another example, Z square with the standard generating set 1001, okay? This is this grid. Maybe I will not show everything now, but you see 0, 0 is our identity, then you have 2 generators, so you have like 2 directions and so on, right? So you've got a grid, right? Okay. So now, what's important here, what you have to realize is that, what I'm trying to do is I'm trying to understand group. So of course, you easily see that it's the same kind of as understanding the Cayley graph, right? Yes.
So I hope I'm not speeding ahead, but the slide says that something about the geometry of the Cayley graph. Yes. So should I be thinking of these graphs as abstract combinatorial graphs, yes, or yes, as metric spaces?
You can do both ways. I mean, you can do both ways, and actually for myself, it's very important to think about them as about metric spaces. And then actually what you can do, you can think about the following metric on the set of vertices, just a set of vertices with the metric which says that the distance between 2 vertices is the number of edges in the shortest path between them. This is the so-called graph metric, and this is very important metric. Actually, this metric, or is, as was mentioned, its quasi-isometric class is kind of invariant for a group. Yes, so you can think in different ways. We will see also another way of thinking about Cayley graphs or about some completion of Cayley graph. Yes.
Thank you.
There is a lot of structure. Yes. Okay. So I want to understand group. So it means, of course, that I want to understand Cayley graph. So, and I asked you a question. I asked myself a question whether, given presentation, my group is infinite, right? So, yeah, I have it on the slide, but I'll tell it now. So, of course, it means what the question, the equivalent question is whether the Cayley graph is infinite, right? Because the vertices are just elements of a group. So, what presentation gives me is the local structure of Cayley graph, right? Because presentation, in fact, tells me that, you know, like, once again, like in a free group, I have no relations. But if I have some relations, it tells me that some words in my group should be the same as identity. So if I go along some words, I should get to the identity. So presentation tells me that some loops should be closed, right? For example, here in this particular example, we know that this is a group given by the presentation that elements commute, generators commute, right? So I tell you the presentation is A, B, A minus 1, B minus 1. Okay? So presentation tells me that if I see a path labeled A, B, A minus 1, B minus 1, I should close this path. It doesn't happen in a tree, because in a tree, the path without backtracking doesn't close, right? But here they should be closed. So idea is that presentation tells you something about local geometry of the graph. And now the question is, so in particular, relators create some cycles, right? Of course, there are other cycles, not only relators, but there are bigger cycles. I can go like this or whatever. But in fact, those cycles are kind of concatenations of smaller cycles, which is also important. Anyway, relators give you cycles. And this gives you some control on the local geometry of Cayley graph, and we want to control the global geometry. For example, we want to say whether this Cayley graph is infinite, right? This is quite typical situation in mathematics. You probably met it in many areas, that from some local behavior you want to deduce some global properties. For example, this is a common theme in differential geometry, or even in differential equations, and many other fields of mathematics. Okay, so this is kind of this question. I will repeat it again, but this is our problem. Okay, so I asked this question. This is equivalent to the question whether a given Cayley graph is infinite, right? So how to approach it? This is kind of geometric question, in a way. I know it's maybe not so convincing, but it can be treated because we have some geometric tools to treat Cayley graph. Okay, so here is one. Here is some additional structure that I can put on Cayley graph. Namely, I can fill in the obvious loops. So for example, this is this Cayley graph of Z square. And of course, it's not contractible. So I think that, you know, I mean, with time, I'm allowed to use some more advanced notions, because maybe some of you could understand this part of the talk. So it doesn't mean that you need to understand the rest of it. I will try to be, you know, merciful, kind of, but just a warning. I will use some notions from algebraic topology now.
Don't worry, we'll beep them out in the recordings.
Okay, I'll use some notion from algebraic topology, and if I'm not, for example, I see here about holes, because I'm trying to make it accessible. But many of you who knows about algebraic topology, about fundamental groups, about maybe homology even, will recognize corresponding terms. Okay, so we'll be able to make what I'm saying more strict. Okay, but so sorry for this language, which may be maybe childish, about holes and so on. But of course this can be translated. So here, this graph, this grid, I mean the graph, the grid is not contracted, right? It has holes. So I can, for example, fill the holes like gluing squares in every cycle, in every short cycle. Short cycle correspond to relators, right? So exactly what I want to do is that for every copy of relator, because you already saw that, I believe you already understand that in the Cayley graph, you have many copies of relators, right? And in every copy of this relator, I can glue in the square, okay? So in that way, I will get something that I call polyhedral complex. Polyhedral complex is made out of polyhedrons, so balls like, polyhedrons, like tetrahedrons, cubes, and so on, in whatever dimension, that are glued together in a way such that two cells intersect among a subcell, okay? This is, for me, polyhedral complex. This will be relevant for what I say next. So, for example, here I can create polyhedral complex, two-dimensional, only using squares, which will be contractible, right? If I fill all the squares, this will be just a plane. It is contractible. Contractible means that this can be deformed in a continuous way to a point, right? And this is an important point from the topological point of view. Okay, so here is another example. This is a Cayley graph, standard Cayley graph of z cube, z to power 3, right? So, of course, if you glue in all the squares, then you will have, for example, boundaries of a cube. You will have still holes inside, but holes of higher dimension, right? You will have trivial fundamental group in algebraic topology language, but you will have non-trivial second fundamental group, right? But what you can do here, for example, you can glue in cubes, all right? And again, gluing in cubes in the standard way will make this space contractible, right? What I want to...
Sorry, why do you want to make it contractible? Just a silly question.
Yes, I do not want to answer this question in a way. I will answer in a moment in a way. Okay. Which means I will not answer it, but I want you to feel that I answered it.
Okay. That's
yeah,
very
no, wait. This is a talk for students, right? I need to cheat a lot, right? I mean, there is no way. I cannot say. Okay. So don't catch me that. Okay. So this is my answer. So the problem whether Cayley graph is infinite is in fact very related to the question whether some obvious, in a way, completion of this graph, whether some complex associated to it, in fact, the complex in which you glue in, you kill the obvious spheres, whether this complex is contractible, right? And I don't want to answer this question. I mean, this is obvious for those who had algebraic topology, who had algebraic topology course, because this is just about contractibility. This is actually about contractibility of universal cover of the presentation complex or some complex related to presentation complex. So this part I want to leave as a black box, but well, I believe you. I want you to believe me. Okay. Contractibility of the universal cover of the complex contractibility of some complex associated to Cayley graph, where you fill in some obvious holes, is very, very close to saying that this Cayley graph is infinite. Okay. Roughly, it's because if you think about simply connected finite complexes, they should look like spheres. So this contractibility is also called asphericity plus simply connectedness. I'm just throwing the terms that are obvious for those who took the algebraic topology course. Okay. So believe me in this, and we'll see what's going on. So now presentation, as I told you, presentation gives you a local structure of the Cayley graph. In particular, it tells you also local structure of this complex, because I want to fill in only the holes that I see somehow obviously. So the problem now is transformed to another problem, which is purely topological, namely, you have a polyhedral complex. Once again, for me, polyhedral complex is that you take a bunch of polyhedrons and you glue them together in such a way that two polyhedrons meet along a subpolyhedron. Okay, so I ask, find local conditions. Local conditions should correspond to this presentation, guaranteeing asphericity of the complex. Asphericity is contractibility of the universal cover. Okay.
Sorry, Damian, can you guarantee that this word is spelled correctly?
That what?
Can you guarantee that the word guaranteeing is spelled correctly?
I'm not so sure.
There's an N missing.
I have no idea.
Before T, there should be an N.
Ah, yes. Okay. Yes, yes.
Well,
okay.
we're talking words in three groups. So that's a generator, which
Yes.
should be there.
Yeah. Okay. Okay. So this is my my reformulation of my problem. I know that there is this black box how contractibility relates to infinite, but this should be kind of obvious if you know something from algebraic topology. So now I'm asking about complex. I have a complex. I just glue polyhedra together. I control somehow locally what's happening, and I want to know that this complex is aspherical, meaning its universal cover is contractible, meaning that if this complex is simply connected, it should be contractible. But there is also more intuitive way. Intuitively, asphericity means that there are no spheres of dimension 2 or more. Okay. So those of you who know algebraic topology, I mean, this all is obvious, and so but I wanted to state it in some.
Sorry, so why is dimension 1 okay?
Because holes in dimension 1 correspond to the non-trivial fundamental group.
Exactly.
If I have non-trivial fundamental group, if my complex has non-trivial fundamental group, I can take the universal cover. Universal cover has trivial fundamental group. And this universal cover is contractibility of the universal cover. In fact, it's what I care about, okay, not the complex itself.
Okay. Thank you.
So spheres. So yeah. Okay. So this is my non-positive curvature. So I will restrict here only to the case of polyhedral complexes. And I ask, give me local condition of polyhedral complex. So local conditions means basically rules of gluing polyhedra together such that I cannot get the spheres inside my complex. Okay? Does this make sense? At least meta
Just
sense.
a quick question. So this definition is posed for what? For polyhedral complexes, yes?
I'm sorry, it's so distorted, I don't.
Yes, I also noticed this. This non-positive curvature is defined on what object? On polyhedral complexes, yes?
Yes,
okay.
Yes. So once again, here non-positive curvature means rules on gluing this polyhedra together, but just local rules. I see only this polyhedra locally that guarantee that what I construct is aspherical. Okay? This is my question. Okay, here is one. I will give you only 2 examples basically. And here is very trivial one, the first one, one dimensionality. I told you asphericity is there are no spheres of dimension 2 or higher. So if I use only one-dimensional polyhedra edges, so the complex is just a graph, right? Then it cannot have spheres, right? By the way, the universal cover of a graph is a tree. In other words, the only graph which has no cycles, this is the universal cover, the only graph that has no cycles is a tree. Tree is contractible, okay? So this is a very stupid condition, but it gives you something. So in particular, this is another way, kind of course, it's a bit weird way of saying why free group is infinite. Because the universal cover because the Cayley graph is contractible. You do not even, in this Cayley graph, you do not even need to fill any cycles, okay? Because there are no cycles. So this is very simple. This is kind of trivial one dimension. So interesting things happens in dimension 2, in fact. So here is dimension 2. And this is the so-called C6 small cancellation condition. It's by now very classical condition. But I give here only the baby version of this. So I tell you, if all your cells, so now you use only 2-dimensional cells, your polyhedra are 2-dimensional, means there are polygons. I tell you, if all the polygons are n-gons with n at least 6, then you cannot create spheres. Okay? And this is a very easy exercise. Hint is that this is Euler characteristic. You can prove that there is no tessellation of the sphere to sphere by n-gons with n bigger or equal than 6. Just compute Euler characteristic. Okay, this is exercise. But so here is an example. So it appears, right? So for example, this is This is an example of polyhedral complex with, made out of cells, which are actually hexagons, right? So what I'm telling you is that however you glue them, you will always get contractible thing unless you create fundamental group, right? Because of course, you can wrap this plane into a torus. It will be non-contractible, right? And not finite. But this is only because you have fundamental group. You have non-contractible loops. If you avoid non-contractible loops, which in algebraic topology terms means that you take universal cover, then you will get contractible. By the way, this is a picture of some window in some mosque. So it appears in nature. But my condition actually is more general. I mean, I allow you to glue your cells however, you can get some branching, okay? So however you glue, this is only one rule, that the only set of pieces that you can use are n-gons with n at least 6. If you obey this rule, so this is local rule because you just see this cell, you glue it, you glue it, you glue it, right? So if you obey these rules, you will get a spherical complex, okay? Observe that 6 is important, right? Because this is a complex glued out of many, many hexagons, but also some pentagons. This is a polyhedral complex. This is a polygonal complex. It's not a spherical. It's actually a sphere. It is simply connected. It's not contractible, right? So 6 is important. There is something inside. Okay. And so this is a condition. This is one version of C of non-positive curvature. There are many conditions like this in dimension 2, many different that I could state, but I will not because the time doesn't allow me. In dimension higher, situation becomes more interesting, much more interesting. So there is a lot of notions of non-positive curvature also in higher dimension that are, let's say, less checkable than this. This condition is, this two-dimensional condition is very good example. So here you have an example actually how it works with presentation. So this is a presentation of a group. You take 4 generators, and actually what you see here in this as relator, you have a commutator of one pair times a commutator of the second pair. So anybody knows what group is it? Exactly. So this is the fundamental group of the closed surface of genus 2. And this is an exercise now. I put it as an exercise or not? No. So this is an exercise now. You can easily see that the Cayley complex of this, meaning you take the Cayley graph and you glue cells inside the, to the relators, you see that the relators are of like length 8, right? So you can check that this Cayley complex will satisfy the 6-6 condition. Okay, this will be polyhedral complex satisfying C6. In fact, C8. But this, okay, so this is an example. So in particular, and actually this is something that happened. Max Dane, who is considered as a grandfather of geometric group theory in a sense, used this condition, this kind of C6 condition, to prove that fundamental group of this surface of genus 2 has nice properties. Because I didn't tell you, but actually this non-positive curvature is not only used to show that the group is infinite, but also to prove that groups have some interesting properties. For example, the so-called solvable word problem. And C6 condition was used exactly for solving word problem for surface group, but by Max Dane. Okay, and moreover, this C6 condition is, or small cancellation condition, is what actually appears in this proof of the Novikov-Adian theorem that I told you. So I told you that they construct infinite free Burnside groups. And this construction, I told you that this construction goes via non-positive curvature. And actually it goes by some version of small cancellation. Small cancellation in general means that you glue cells in a way that's such that the intersection is small compared to cells. So this is why I mean, for polyhedral complexes, for the C6 condition that I told you, is that the length of the polygon is big because I always glue along one edge. But sometimes it can happen that you glue along more than one edge and then small cancellation. And this is what happens in this case of Burnside group. And in this case, in fact, small cancellation simply means that you control the way you glue two cells. Okay, so this is how this kind of non-positive curvature plays role in this theorem. And it is believed that, and actually this is ongoing work, then using some other small cancellation on some other non-positive curvature, you can go lower with M, or even maybe construct these finitely presented Burnside groups that I mentioned. And here is one more precise question, also open big conjecture, also related to this industry of controlling groups by controlling the curvature somehow of the Cayley graph. There is a class of arting groups. Those are groups defined by such relations. The relations, they are called sometimes generalized braid relations. So you have generating set S, and then you have ST, 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 word of this length. You declare that this word is the same as T, ST, STS. So in particular, some of you may know that STS equal TST is the so-called braid relation. And in fact, arting groups are generalizations of braid groups. Braid groups are very common in physics and in many areas of mathematics. And arting groups, okay, they are known, they are finite, as there are infinite, I'm sorry. However, there is still a widely open conjecture that some particular complex associated to these arting groups, so you have very precise presentation, you have very precise complex. This complex is just that, as I did in case of Z2 and Z3, that you simply kill some obvious spheres. And the conjecture is that this complex is contractible. And this is widely open conjecture with a lot of attention now. And one way of proving this belief is that you have to use non-positive curvature in some way. So you have to say that this complex, the presentation complex, or actually this Salvetti complex, is non-positively curved in a way. And this should give you that it is contractible. So another problem to think about for you. And I think I thank you for your attention. Thank you very much.
Thank you so much. Yeah, thank you very much indeed for such a brilliant talk. I thoroughly enjoyed it. I hope you guys as well. So
I did. Okay.
So any questions? Go ahead.
So you mentioned that the C6 property has been used to solve the word problem. For the genus 2 fundamental group.
Yes, that's correct.
So my question would be, how does a geometric condition like that translate to an algorithm for solving the word problem?
Yeah, this is a very good question. So, because algorithmic properties. So, okay, so first of all, maybe I ought to explain what's the word problem for groups to rest of you. So given a presentation of a group, as you saw, presentation of a group is just sometimes very simple data. In this case, in the case surface group, this is a finite data, right? For 4 generators, 1 relator. And then the word problem, it can be asked for any presentation. Ask the following: having a word in generators, is there an algorithm deciding whether this word represents a trivial group? Trivial element, sorry, right? Okay. So this is the word problem. It's very well-known problem. There are groups, even finitely presented groups, with unsolvable word problems. So you cannot decide. You cannot. I mean, the result is that you cannot invent algorithm that given a word will tell you whether this word represents trivial element or not. Okay. For these groups, there exists such algorithm, and algorithm is actually very geometric. And algorithm works as follows. So deciding whether a group element, whether a word is trivial, is asking about whether the word in the Cayley graph gives you a loop, right? So now, so you are given a word. Now suppose that this gives you a loop, okay? Then actually non-positive curvature this non-positive curvature, this C6, tells you that if this was a loop, then you can fill it with cells. Cells are just relators, and there is a particular bound on the number of cells. Actually, the bound is linear in the length of the length of the word. So once again, so do you see? You probably see already the relation. So now we reduce the situation to the following: you give me a word, I already know how many relators at most I need to fill this word. Okay. So what I do now, I just check all of them.
But don't you have to consider conjugates of relators too? Does
No.
that not present a problem?
This is just a technical. This is just a technical issue. I mean, every cycle in the calligraph is labeled as a relator. But of course, I mean, if you write it as a word, it can be, it can be from identity. You go somewhere, you go the cycle, and so this is conjugate. No, but this is not a problem. You can also, you take a word. It should be a loop based at identity. So everything happens in n ball. So you just consider finitely many things. Yeah.
Anybody else in the room?
Yes, I wanted to ask this notion of non-positive curvature in the context of this geometric group theory maybe somehow related to the notion of non-positive curvature in a differential geometry, and I would be interested in which kind of curvature is most close to it: sectional, scalar, Ricci, or...
Yeah. This is very related. I would say that this is sectional curvature. So in particular, I told you that my non-positive curvature are local conditions implying asphericity. So this is reminiscent of Cartan-Hadamard theorem, telling you in the manifold world, telling you that if you have a manifold with sectional, non-positive sectional curvature, then its universal cover is contractible. And actually, we call our theorems, I mean, if we can prove some theorems like this, that universal cover of complex with this and this properties is contractible, we call it Cartan-Hadamard theorem. So,
all right.
Yes, and maybe one more question. Is it possible in this context of negative sectional curvature to have finite volumes, or it always is infinite volume of a manifold?
Volume of what?
Of a manifold.
Yes. I mean, yes. Okay. Yeah. I mean, even in the case of surface. Yes. I mean,
I'm always confused about this. In some sense, my intuition is that in the negative curvature you have more space, and somehow this is very ample. But I don't know whether my intuition is correct.
I think it is. I mean, so for example, non-positively curved groups, or even better, negatively curved groups should have very large growth, exponential growth.
Yes, for example, yeah.
So it's one of each. I mean, as I defined it, non-positive curvature as some conditions, it's very, let's say, vague definition. And this is what we do. In fact, I mean, we just look for some conditions that resemble kind of non-positive curvature, tailored to some applications that we want. So, but there are properties that are shared by various notions of non-positive curvature. There are properties that are maybe not that shared, but large growth, but big growth is one of the properties that usually happens. Yes, and in particular for negative curvature, definitely.
Okay, thank you.
So Adam, I understand you're happy. Oh.
Yeah, so one more question from me. A few times during the talk, you mentioned gluing in the obvious gaps. Yeah. And they are very visually obvious once you draw a graph, but can you determine in general which of those are? Because if you fill in too much, then that can create additional spheres, and I think that's...
Yeah, that's true. No, I cannot. I mean, yeah, I know this is a vague question, but I wanted to know, this is for sake of presentation, but I mean, of course, not always you can do it. and not always you can do something with your. So this doesn't work. Okay, but not always you can do it, but sometimes. But my point was that sometimes you have some obvious complexes, and we would like to apply it there. And
Okay.
in many cases, no, this is not that I have some magic tools that I cannot make it more precise. This is really that I want to have non-positive curvature for some particular complexes. But it's often the case that you know somehow what to glue in for various reasons. But yeah, but in general, no.
Anybody else? Anybody on the Zoom? Come on, guys. Use your chance. I see no raised hands. Okay, so there are no more volunteers. Let me ask you some questions.
Okay.
I remember some time ago, Paul Baum went to visit you in Wrocław because of your involvement in this Gromov's monster group.
Correct.
Could you say a little bit about these expanders and Gromov and all that stuff?
Yeah, I can set. Yes, I can tell something. I
even have it on slide.
no, I don't have it on slide, but this is very related actually. I'm simply.
This month was okay now.
I mean, yeah. Oops, it doesn't. I mean, simply I'm not very clever, so I'm basically working with not always with the same. So actually, so I told you the following, that if you have some property of a presentation, then you know that the group that you construct is infinite. So this is one condition, this small cancellation condition, and this is the presentation that satisfies this condition in a way. So actually, this small cancellation condition gives you much more control on the group when the presentation has this property. In particular, it allows you to construct groups. You simply write, but because maybe it was not mentioned, or maybe it was not told that this was not that obvious, but I told you there is a question whether a given presentation give you infinite group. But this question is, I mean, it has practical consequences, right? I mean, because presentation is just data. You just write down, you just write down the presentation, right? Whatever. But then the question is what? So what this presentation, what property it has, right? But writing presentation is a way just of defining group. And now, if you write your presentation obeying, for example, some small cancellation rules, then you will be sure that this group has some properties. One is that this group will be infinite, but actually this C6 small cancellation condition gives you also that this group will have many other properties. For example, some of them will be Gromov hyperbolic. This relates to this negative curvature question that was posed. Some of them will impose that actually the relators will be embedded in the Cayley graph. Because if the group collapses, if you write the presentation of a trivial group, that it means that you have maybe very, very fancy relators, very, 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 very long words, but actually they are all trivial, right? So it means that the relators collapse in the group itself. But this presentation tells you that they don't, that they really exist. So in particular, this allows you, this C6 small cancellation conditions allows you to embed some objects into your group, to embed some particular graphs into the Cayley graph. And this is what Jacek refers to, because yes, Piotr refers to. Both of you probably refer to this. So because there are some interesting, from different point of view, there are interesting metric spaces. Piotr mentioned expanders. Expander graphs are very interesting infinite graphs that are used now, that have practical and actually coming with a lot of money applications. And now, so there are some exotic metric spaces. Now groups, as you saw, and I was following the question here, groups can be also seen as metric spaces, as graphs with some metric. But of course, groups are much more rigid. Groups have much more symmetry. So the questions that were posed at some point around this Baum-Kohn conjecture, whether you can have as bad groups as you can construct examples of metric spaces, in particular groups that contains these mysterious expanders. And this C6 condition allows you to construct such groups. Simply you take such expanders and you label them by your generators, and this gives you group presentation. And if you label them appropriately, meaning that this C6 condition is satisfied, then you know that these relators are embedded into Cayley graphs, meaning that expanders are embedded into Cayley graphs. So this is exactly this. And actually, I was using this C6 condition.
This is wonderful. I don't want to dig into non-commutative geometry right now, but let me tell you, it was a very big thing. And because people were really unsure how to make sure that these groups exist. And for these groups, you could construct coefficients such as the Baum-Kohn with coefficients would fail. So that was really a big deal, and there was a lot and lot of seminar discussion about it. So when Paul Baum came to Warsaw, he immediately demanded that he be introduced to Damian and go to see him. So as I remember. Okay, one more question I have is, I understand that you are all the time here in the realm of discrete topology. So all your groups are discrete.
That's correct.
Would it be of any use to think about them with some non-discrete topology? I don't know how, just I'm used to locally compact house of groups.
Yeah, I mean, yes, I mean, yeah, I mean, I'm not working in non-discrete groups at all. However, of course, discrete groups appear naturally in some non-discrete contexts as some, for example, some lattices in automorphism groups of some complexes. So I mean, this non-positive curvature also appears for non-discrete groups, at least is applied there. But as far as I know, maybe more via some indiscrete, in indirect way. But yeah.
Okay. And I'm wondering, Mariusz, what do you think? I'm wondering, we have, for instance, very beautiful versions of non-commutative permutation groups. So when I saw these Burnside groups, it immediately occurred to me, or vice versa, we can think about these discrete groups and very convolution statistical algebras as abelian quantum groups, as abelian compact quantum groups. And it would be interesting whether they are contractible, you know, using Borsuk-Ulam and so on. It's just, by the way, sorry, that's about enough. I think we deserved lunch, so let us thank Damian again for, oh, you want?
Maybe one more question, if I could, about this technical detail about the undecidability of word problems. So when something is undecidable in this context of algorithmic theory, it is always for some decision problem, given some n, whether it belongs to some set, and whether this set is recursively enumerable. So in this context, what is fixed and what is varying? The group is fixed, the word is varying, and you ask for an algorithm which would solve this problem uniformly in all words, but the group is fixed?
Yes, that's correct. I mean, you are given group, I mean group meaning you have presentation, for example, and you are asked whether for this group exists algorithm such that on input, if you input the word, it spits out yes or no. I mean.
Okay, thank you.
Yes.
Okay, so it's time to thank our speaker again for a very brilliant talk.
Thank you.
We have also people clapping.
Okay, thank you. I guess.